This video is in a chapter of vectors in vector spaces, and we are introducing the concept of distance, angles, and projections. In one of the previous videos, you have to go a bit back now. I think I proved all this when I introduced the concept of norm. We saw that the norm satisfies these three properties, or these three laws. Okay, so one, for any vector in the vector space V, the norm will be 0 or positive. If the norm is 0, it happens if and only if the vector is 0. Okay, so this is one of the first properties of the norm. The second property is for any vector in the vector space V and k scalar in the field, the scalar product k times u, the norm of the scalar times the vector, is equal to the norm, to the absolute value of the scalar times the norm of the vector. And that's the second property. Third property, any vector u and v in the vector space V satisfies what we call the Minkowski inequality. I think I called it Minkowski inequality or triangle inequality. So in the previous videos we introduced the concept of distance in a vector space, and we said that the distance between two vectors is defined as, at the end of the day, the norm or the absolute value of u minus v. So we have a vector like this, u, a vector v, and the distance, this will be u minus v, the distance between the two vectors. Okay, so in this video, quickly, I want to show that this concept of distance has exactly the same properties as the concept of norm. Okay, and that it follows this, it satisfies these properties. Okay, so I'm going to use the properties of the norm. Okay, okay, but the notion, the concept of distance will have some other properties where I'm going to use the norm properties to prove some of them. Very first property, so I'm defining the distance between two vectors as u minus v, absolute value. So very first property, the distance between two vectors will be always 0 or bigger than 0. And the distance will be 0 if and only if vector u is equal to vector v. The distance between vector u and vector v will be equal to the distance between vector v and vector u, so they are symmetrical. And third, the concept of distance will also follow the Minkowski inequality or triangle inequality. The distance between u and v is less or equal to the distance of uw plus the distance of wv. Okay, for all vectors u, v, and w in the vector space. So now we are going to prove that these three properties, they are true. So the very first one is the distance between u and v is bigger or equal to 0. But we define the distance between u and v as the norm of the subtraction of vector u minus vector v. So u minus v, we are going to get a new vector here, okay, and we have a norm here. Okay, So since the distance is also a vector, okay, and we are in the normed space, so it follows the first property of norms that says any vector, the norm of any vector will be bigger than 0 or 0, and it will be only 0 if the vector is 0. Okay, and that's the case here. So it will be only 0 if the vector is 0. But how can the vector u minus v be 0? Only if u is equal to v. So this one is proved using simply the first property of norms. Now we want to prove this one. So we want to prove that the distance between u and v. Okay, let us see first what is the distance between u and v. The distance between u and v, by definition, will be the norm of u minus v. Okay, but what is u minus v? U minus v is the same as the norm of minus 1 times v minus u. We just exchange this. And this is the second property of norms. Okay, just check the second properties of norms. Okay, so this is equal to the absolute value of the scalar times the vector. But the absolute value of minus 1 is 1. So what we have is v minus 1. Okay, let us rewrite v minus 1 under the definition of distance. This will be the distance of v u, right? So what we got here is the distance of uv is equal to the distance of v u, and that concludes the proof for the second. For the third property, I'm not going to get into details. I'm just going to check the equality. So what is the distance between u and v? Well, that's the definition of distance, okay? The norm of u minus v. Okay, but u minus v, I can add and subtract w, right? I add w and subtract w. So that will be u minus w, and I associated these two, plus w minus v. You can cut these two, right? This one, and you'll get u minus v, okay? So this is correct. Okay, so this is the norm using Minkowski inequality. So this will be smaller than the, so it's like a plus b is less or equal to the norm of a plus norm of b. Okay, so I can use Minkowski inequality here. But what is the norm of u minus w? Following the definition, that's the distance between u and w. What is the distance between, what is the norm between this vector w minus v? That's the distance between w and v. So the conclusion is distance of uv is smaller or equal to the distance of uw plus distance of wv. So distance of uv is smaller or equal to the distance of uw plus distance of wv. And that concludes the proof for this third property of distance.